Hey there, and welcome to Chapter 8. And we're going to start with Chapter 8 talking about reviewing some of our ideas with review proofs with sets. Oh, that's the second day's lesson. Sorry about that. Just a reminder, your Semester 1 notes, since we're switching over into a new Google Classroom, your Semester 1 notes are going to be available in course materials at the bottom of the page for the entirety of Semester 2. I'm not linking to every single video just because Google Classroom doesn't let you attach quite that many things, but the guided notes, the PDFs are all available in the course materials. If you're interested in a video or one of those things like that, I am happy to go back and share out whatever materials you would want to rewatch. So, we're going to start today by talking about proving with sets. So, we see here in number 1, prove that this is the complement of A intersect B is equal to the complement of A union the complement of B. So a couple of things quick to review. Let's start with the symbols. Is that we have our intersection and our union. So union, which means that it's in A or it's in B. Intersection, which is A and B, so it has to be in both sets to be in the intersection. Whoop. The complement, which is everything that's not in the set. And then you'll also see subtraction, which just means that it's in A but not in B. Now, another nice review that hopefully we can remember is that whenever we want to prove with sets, so if I want to prove that two sets are equal, I need to do a first step, which is to show that A is the subset is within B. So what that means is that if A is in A, that automatically implies that A is in B for every element of the set A. And then we have a second step, which is to show that B is a subset of A. Again, that every element in B also therefore must be in A. And once we prove these two, that means that A must be equal to B. And so when we look at number 1, prove this statement, we're going to start with our first step, which is we want to prove that A intersect B, the complement of that, is equal to the complement of A union the complement of B. Now, the way that we're going to start a lot of these is we're going to use this type of notation, which is to say that there is an element in that first set, and we want to show now that this element is also in the second set. And for these, we're going to use our terms for involving sets. So if I have A is in the complement of A intersect B, that means that X is not in the intersection of these two. That means that X cannot be an element of A, and also that X cannot be an element of B. And that's just an or, because it could be an element of one or the two. If it's not in the intersection, that means that it isn't in at least one of them. So these ands and ors are really important to pay attention to. Because what we can say then is that if X is not in A, that means X is in the complement of A, or X is in the complement of B, which is what we want to show. That means that X is an element of the union of the complements. So what we've done now is that, therefore, we have intersect B complement is a subset of the union of the complements of A and B. So that's our first step done. Our second step, sometimes these steps will be very similar, sometimes they'll be very different. In this case, again, we want to prove the subset going the other way. So we want to say that X is an element of the second set, which means that X is in A complement or X is in B complement. That means that, again, if X is not in A and X is not in B. Now, this is where we have these ands and ors. That means that if X isn't in A, that means it's not in the intersection. If X isn't in B, that means it's also not in the intersection. So the union is always going to be the bigger set, and then this one is going to be the and also it's in both. So then here, we can say that that means, oh, well then X must be in the complement of A intersect B. Hence, that means that this second set is a subset of the first. Finally, that means that the sets are equal. So hopefully this feels somewhat like review from previous chapters. So some of the homework for this unit will look very familiar. Some of it's going to be a little bit trickier, involving some of our new notation, though you'll notice that sometimes it's just about proving a subset one way. So what we'll do here is prove that X, where X, M, and N are integers, prove that all the numbers where Mn divides X is a subset of the intersection where M divides X and N divides X. So what we want to do here is we're going to say let M and N be integers, because that's given there, and we're going to say that there is an element in that first set where this is also an integer, N divides X. So, and then our goal is to show that this element A must be in this intersection of our second sets. So since we know that A is in this set here, that means that means that Mn divides A. That's what it means to be an element of this set. So I will then create an equation from there saying that A is equal to Mn times P, where P is an integer. Now I'm interested in M divides X and N divides X. So if we know that A is equal to MNP, then we could say that A is equal to N times NP, and we can say that A is equal to N times NP. Now we'll do our normal division rules that you can probably, hopefully, start to guess from here. We're going to say that, all right, well, that's an integer by closure. And MP, we can say is equal to C, which is an integer by closure because it's just multiplication. So then A is equal to MB and NC, which means that M divides A and N divides A. So therefore, A is an element of both the set where M divides X, and so the intersection of the set where N divides X. And that's all we need to show that it's a subset, is that it must be in this first set, and therefore it is also in this last set. Let me know if you have any questions, and as always, set up appointments, nominate problems in the forums, and I am available for any questions as we keep going into semester 2.